Hello everyone. Today we are going to talk about maximum and minimum values of a function. One of the most important applications of derivative is to find the points of a function where it takes a maximum or minimum values. And there can be absolute maximum or absolute minimum values, or there could be local maximum or local minimum values as well. Also, we use the terminology as points for the x coordinates of such points and values for the y coordinates of such points. So here is the first definition. Let a be a point in the domain of a function f of x, then f of a is the absolute maximum value of f on its domain D if the value f of a, if the value of the function at a, which is f of a, is always bigger than or equal to all other values of x in the domain. So f of a is bigger than or equal to f of x. An absolute minimum value of a function is if f of a is less than or equal to f of x for all other points x in the domain, then such a point is called an absolute minimum, and the value there, f of a, is the absolute minimum value. So a local maximum value of a function f of x is if f of a is greater than or equal to f of x for all x nearby a. So this is a local part of the domain. And a local minimum value of f of x is if f of a is less than or equal to f of x for all x nearby a. So look at the picture here in the example. This is an example where the function is defined from -3 to 5, so that's the domain of the function, and the range is -1 to 6. So as you see, it is defined from -3 to 5. So the largest value that the function takes here is happening at -3. So then -3 is called the absolute maximum point, which is the x coordinate. And look at the value. The value is 6. So 6 is called the absolute maximum value of the function. And then look at 5. At 5, the function takes the value -1. So that -1 is called the absolute minimum value, and 5 is called the absolute minimum point. And then you see there are in between, there is a local max and local minimum as well. Like at 2, x equals 2, there is a local maximum value. So 2 is a local maximum value because the value of the function is 4, and around 2, 4 is the largest value, but it's only around 2. And then look at x equals -1. So the value of the function at -1 is +1 because it's mapped to +1. So that is a local minimum value. So that means that nearby -1, the function takes the minimum value as 1. But as you see, if we go further away from -1, let's say when we come around 5, there are smaller values. So as you see, at -1 there is only a local minimum, and that local minimum value is +1. And then in a similar analogous way, at x equals 2, the function takes locally a maximum value, which is 4. But as you see, if we go nearby -3, then there are larger values for f. So only around 2, the function takes a local max value. So these are how we can explain local max, local min, absolute max, and absolute minimum values and points. So the points are for the x coordinates, and values are for the y coordinates. Now, there is another definition which is called a critical point. So a critical point of a function is a number x equals c such that the derivative is equal to 0 at c, or the derivative doesn't exist. So the derivative equals 0 at c is the picture on the left. So you have a graph like this, and then when you sketch the tangent line, graph of the tangent line, as you see, the tangent line is horizontal. When the tangent line is horizontal, it's neither going up nor down nor going down, so neither positive slope nor negative slope, so it must be 0 slope. So if a tangent line is horizontal, the slope is 0, which means the derivative is 0 there. So this point C is one example of a critical point. So if the tangent line is horizontal, then the derivative is 0, then that's a critical point. Another example is the one on the right, this right picture. So at this second picture, the derivative from the left, which is actually the slope of the tangent line from the left to the graph, and then the derivative from the right is the slope of the tangent line from the right. As you see, they are shown with these red tangent lines. From the left, it's a positive slope. From the right, it's a negative slope. So they cannot be the same. Then the derivative will not exist there. So that point C is also another critical point example. So we have critical points. Either the derivative is 0 at that point, or the derivative doesn't exist at that point. So geometrically, a critical point is where you have a horizontal tangent line, or you have a broken graph in the picture. Like if you look at the graph of the function, then there is a broken graph at the critical point. Algebraically, look at this example. Let's say we have this function x cubed minus 12x. Now, if we take the first derivative of this function, then and if we set it equal to 0, it will give us some critical points. So take the first derivative, which is 3x squared minus 12, and set it equal to 0. Then factor 3 first. So 3 times x squared minus 4. And then x squared minus 4 can be also factored as x minus 2 times x plus 2. So if this product is 0, either x minus 2 is 0 or x plus 2 is 0, which means either x is 2 or x is minus 2. Then these 2 points are critical points of the function. And if we sketch the graph of this function at 2 and minus 2, you will see that the tangent lines are going to be horizontal. There is a theorem by the name of Pharma. So if f of x has a local maximum or a local minimum at a point C, and if the derivative exists, then f prime must be 0 at that C, and C must be a critical point. Like, look at this picture here. Like, there is a local maximum at minus 1, and there is a local minimum at plus 1. And look at the tangent lines. They are both horizontal, which means the derivatives are 0. So, at these minus 1 and plus 1 points, these are C equals minus 1, and the other one is C equals plus 1, let's say. The derivative is 0. And as you see, the derivative also exists, but minus 1 is a local maximum and plus 1 is a local minimum. So this is what Pharma's theorem says. So if f has a local maximum or a local minimum, and if the derivative exists, then f prime or at C must be 0, then x must be also a critical point. So a local maximum or a local minimum, and if the derivative exists, that point must also be a critical point. So here is this example, x cubed minus 3x plus 1, which is the example in the picture, almost the picture. Yeah, it's the picture. So at x equals minus 1, there's a local maximum. At x equals plus 1, there's a local minimum. So when you take the derivative of this function, it's going to be 3x squared minus 3, and plug minus 1. 3 times minus 1 squared minus 3 equals 3 times 1 minus 3, which is 0, and plug 1. F prime at plus 1 is going to be 3 times plus 1 squared minus 3, which is 3 minus 3, which is equal to 0. As you see, the derivative is 0 at both of the points. And these 2 points are local maximum and local minimum also. Now, but there is a remark here. We have to be careful. Like, all local maximums and local minimums are critical points, but not all critical points have to be local maximums and minimums. So this is what this is saying. For instance, take this function x cubed. Take the derivative 3x squared, set it equal to 0, then 3x squared equals 0. This is only possible for x equals 0 or c equals 0, let's say. Now, at 0, there's a critical point, but look at the picture of x cubed. Look at the graph. Well, there is neither a local maximum nor a local minimum. Still, the derivative is 0. So as you see, critical points are points where the derivative is 0 or the derivative doesn't exist. They could be local maximum or local minimum or neither. But all local maximums and all local minimums are critical points. But not all critical points are local maximum or local minimum. So this is what this remark is saying. And then there's an extreme value theorem. This theorem is also important, and it has some nice uses which we will also deal with. So this extreme value theorem states that if f is a continuous function on a closed interval a to b, then f takes an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in the interval a to b. Like, here are some possible pictures. Like in the leftmost picture, there is an absolute maximum here, and then there's an absolute minimum here. So the absolute maximum and minimum can be in the interval, or look at the middle picture here. The absolute minimum value can be at the left end, as you see, and the absolute maximum value can be achieved at the right end. So absolute maximum and minimum can be in the interval or at the endpoints. Or look at this third picture, which is the rightmost one. The absolute maximum value is happening in the interval, but look at the absolute minimum value. It's happening at one end of the interval. So it can happen anywhere in the interval or at the endpoints of the interval. So to find the absolute maximum and absolute minimum values of a continuous function on a closed interval a to b, we check the critical points and we check the endpoints because of this extreme value theorem, and this is called closed interval method. So we first find the values of the critical points. Like, look at the first left picture, like the absolute maximum, the derivative is 0 there, so it's a critical point. Or look at the absolute minimum. Well, it's happening at a critical point, so. Or look at the third picture. The absolute maximum value is a critical point, so it's a critical point, and we check first the critical points where derivative is 0. Or the second picture and the third picture, as you see, absolute max and absolute minimum in the second picture is happening at the endpoints. Or on the third picture, the absolute minimum value is happening on the endpoint. So we check both the endpoints and the critical points, the values of the critical points. Then the largest one of these values obtained from checking the endpoints and the critical points will give us the absolute maximum value. The smallest one of them will give us the absolute minimum value. For instance, take this example. Let's say we have this function x cubed minus 3x squared plus 1, and let's say our interval is minus 1 to plus 1. Now first find the derivative. The first derivative will give us 3x squared minus 6x equals 0. First factor 3x, it's going to be 3x times x minus 2 equals 0. And then x equals 0 or x equals 2. But if we look, only x equals 0 is in the interval minus 1 to 1, but 2 is not in this interval. So we only take care of x equals 0, but we ignore x equals 2 because x equals 2 is not in the interval. So then we find the value of the critical point 0. So we plug it to the function. The function is x cubed minus 3x squared plus 1. Plug 0 there. 0 cubed minus 3 times 0 squared plus 1, which is equal to plus 1. Okay, so this is the critical value at 0. Then check the endpoint values, which are, the endpoints are minus 1 and 1. Put them into the function. So if you put or plug plus 1, we are going to have 1 cubed minus 3 times 1 squared plus 1. So 1 minus 3 plus 1, which is minus 1. And then plug minus 1 into the function. We are going to have minus 1 cubed minus 3 times minus 1 squared plus 1, which gives minus 1 minus 3 plus 1. That gives minus 3. Now we have three values here. Plus 1, minus 1, minus 3. The largest one is plus 1. So plus 1 is the absolute maximum value. The smallest one is minus 3, and minus 3 must be the absolute minimum value. Okay, so at minus 3 is the absolute minimum value, and plus 1 is absolute maximum value. So absolute minimum point is minus 1, absolute maximum point is x equals 0. And this is how we find absolute maximums and absolute minimums of a function on a closed interval.